Hey guys, welcome back. So today we're going to go over all these tabs in my Excel sheet. We're going to answer how much power does each individual component pull, and the two big questions. What is the average amp draw for one race, and what is the peak amp draw? Because both of those numbers matter. The average is for battery size, but the peak, the system's got to be able to supply that peak power. So let's take a look. So we already covered the coils in the last video, so we'll just summarize. The average draw is 13 amps. Our peak draw is about 39 amps. Now, let's go to the fuel pump. We're going to start down here. So our fuel pump, what I did, we're going to run a 6 gallon per minute pump at about 95 psi. So I used a calculator online and plugged in the numbers, and that takes about a quarter horsepower to create that much flow at that pressure. That's hydraulic horsepower. Now, for pump efficiency, we're assuming a terrible 30% efficiency. We hope that our pump is better than that. But we are pumping thin fuel, and I don't really know what the efficiency is, so I assume something terrible. Because of that, we also put the belt and pulley, because we're going to have to run that, so we got that at 98% efficient. And the electric motor, we got that at 75% efficiency. So when you take all that into account, what you find is our shaft horsepower going into the pump is about 0.83, and that's because of the terrible efficiency. And that number just goes up from there. Doing the pulleys bumps it up to 0.85, and the electricity going into the motor to create that shaft horsepower due to the motor efficiency, we're up to 1.13. So converting that into watts, that's 857 watts, and if you're supplying 17 volts, that's 50 amps. So okay, at 17 volts, the electric motor is going to pull 50 amps. Now, like I said, it's probably worst case. Hopefully it'll be less because the efficiency is not so bad. But let's roll with that. We already covered our ignition. Let's jump over to the water pump. This one's pretty easy. I found a water pump that pulls, it says 10 amps max, but typically 9 amps. But hey, it says 10 max, so let's go with that. We're just going to assume that we run the pump at full speed all the time, which is probably what we're going to do anyway. So that's real simple, 2.3 amps. We'll go to our fan. Same thing, it's a cooling system component, so we're just assuming 100% cooling at all times. We may not actually do that, but I want a system that I have full cooling, and I take that into account. Next tab is our wideband. So widebands, these things start off pulling more current because it's got to heat the sensor up, but after that, they don't run as much. So you can see we backed off on that. We ended up with 0.32, so not too much. Let's see. Next is our ECU. We just did an amp. I couldn't actually find a number for this, so I just assumed 1 amp. That's probably close. That gives us 0.23. Next we got our VVT. I don't actually know this number either, so I just put an amp, and it only comes out to 0.23, but I mean, it's not much. That's like a quarter of an amp hour, so if we're off a little bit, not a big deal. And let's see. The pre-stage and staging, we've got 20 seconds for each. So that's basically 1 minute total. That's, I doubt we're going to do that much, but we're trying to budget for worst case. So that gives us 0.13. Not really much anyway. Go to the injectors. We're doing 1.2 amps per injector, and we do have 4 injectors. But most of the time the duty cycle is low. You can see here in our graph that we actually took duty cycle into account when we were doing our calculations. It only ends up being 1/10 of an amp hour. Not much. Last thing is our running lights. We just did 0.3. We're going to do an LED conversion. It ends up being some tiny number. All right, so that's our pieces. Now let's go into, we kind of got 3 things. We got a 13.8 volt system, a 17 volt system, and then we'll look at the battery. So let's go to our 13.8. So here's our amp numbers. These are the peak amps. Well, actually in these parts, the peak and the average are basically the same. So, sorry, my focus is being sad. So we look down here, here's our peak and our average, or around 43 amps. Now I'm putting a factor of safety of 1.9 on this. So that means we're calling out for an 82 amp design output. Now the pieces that I'm using, I got to put them in parallel. They're rated for 25 amps each, but I'm derating those some just for reliability. So here I assumed that we run them at 85% of their 25 amp rating. So 4 of those, we end up with 85 amp output. So that actually gives us a factor of safety of 1.96. So this thing's basically double what it actually needs to be, which is good because if we ever add anything in the car, we've got that extra amp capacity. Here you can see the weight of these parts is about 1 pound a piece. These are pretty efficient, 96%. And then check this out. Here's our input current at the design output with a 12.4 volt battery supply. So we'd actually be feeding these things with 95 amps. Now that's to get the 85 amp max output. However, if we just look at our expected numbers without the factor of safety, then we're looking more at about 50 amps going into this thing. And then that's from the battery. And then down here at the very bottom, this is our amp hours. So since we're not going to take an hour to make a pass, it's only going to be a few minutes for all the driving. It ends up being 5.4 amp hours coming out, or that's the output to like feed everything. So from the battery, it ends up being 6.25. So not too bad. Let's jump over to the 17 volt system. So here you can see our coils. We have different numbers for average and peak, but everything else, the averages and peaks are the same. So we have to take that into account. But these are big numbers. You can see compared to that other one, we're looking at big numbers here. So our peak output when racing, we're looking at 95 amps. And again, that's at 17 volts, but an average of 80. So we threw a factor of safety of at least 1.3, and that puts us at a design output of 124 amps. I'll admit I kind of want to bump that factor of safety up, but let's run with that for a second. So here you can see we have to spec 7 of these guys. We're using 20 amps a piece. They're rated at 22, but we're derating them a little to 20. So that gives us 140 amps of output, which means that our factor of safety for the maximum current, we've got a 1.47, and for the average a 1.75. So that's actually not that bad. These converters are 0.73 pounds. So we end up with about 5 pounds of converter. Assume 95% efficiency is what they publish. Look at these numbers. This is high. So the input current at the design output, this is how much current the 17 volt system pulls when it's running at its designed output amps and you're feeding it with 12.4 volt signal. You get 178 amps, basically 179 amps feeding into this thing. Pretty damn high. And then you can see input current at the expected peak output is lower, 137, and then with the average number it's 115. So that's 115 amps coming off the battery. And last but not least, we can see our amp hours. We're looking at 5.5 amp hours from the 17 volt system. That's at 17 volts. When you convert that to battery voltage, it ends up being 7.75. So if we go to here to this last piece, total amp hours per pass, we're going to end up, when we add those two numbers together, you get 14. And our average amp draw for the whole time is 60 amps. But our peak, look at this number, 187 amps. This is the killer. Those peak amps are so high. And you can see our peak amps in their 17 volt system is 137 with 95 going out. And then going into the 13.8 at 50, coming out at 43. Like we said, 187 amps total coming out of that battery. Jesus, that's a lot of amps. And that's actually 2.3 kilowatts. So wow, that's a lot of power. So that was the point. We did all this stuff. This is worse than I thought it would be. But this is the reason we did this. It took so long. But my car is going to pull 187 amps. There's no headlights. There's no brake lights. There's no HVAC, no stereo. I mean, this is just the bare bones stuff. And we're pulling 187 amps. So if I go back and look at what I was planning on doing, I had planned to just keep the stock alternator and then put a battery. Then I looked at putting a bigger alternator, and I kind of came to the conclusion that I probably didn't need it. But that's clearly not the case. I mean, 187 amps, like, there's pretty much no alternator I can put on my car that's going to keep up. And the ones that do, like the people that make alternators that'll put out that much power, they don't like high RPMs. So you have to pulley them to where they only charge at high RPM. They're not going to charge at idle, which kind of defeats the purpose of having an alternator. So there's not really a great way to solve that problem. But that really puts things into perspective, 187 amps. So now I know, not even starting the car, the starting amps are going to be high too, but just running the car, you're going to see some really high current draw from that battery. So we're going to use that info to spec out our battery to make damn sure that, you know, whatever we put in the car is going to meet these requirements. And like we said, a lot of this stuff we did were peak loads and looking at, you know, worst case when you're racing. But that's how you design stuff if you want to know it's always going to work. You got to look at your worst case loads. You know, you can't just look at averages. I mean, if you tried to size a fuel pump like that, the average fuel flow rate is basically just above idle at a drag strip, maybe 50 horsepower worth of fuel or something. That doesn't work, because when you're racing, you're burning a lot of fuel. So you got to look at this stuff. And this took a long time to do, but it's definitely paid off. I've actually gained quite a bit of insight into efficiencies of how these systems work. Like, I'd always wanted to try a high voltage system, but I didn't know like how much weight it would be, how many amps it was going to pull. And it's kind of a good thing I never tried this before, because I would have never had the electrical system to support this. So it's kind of good news that our battery is going to, I think our battery is going to be able to support this. So that's kind of cool. But, you can see here, I think we already talked about it, but, it's rated for 280 amps. We're going to need those. So I think we're going to be good. But hope y'all like this. This gives you some insight into a little bit of electrical engineering for speccing out a race car and knowing that what you're putting in the car is going to be adequate. Anyway, until next time, y'all take it easy.